Yeah. And you can include images. Apparently, like some people were confused if you can include images or not. Images are allowed as long as they're not offensive. All right. What are the topics that could potentially be on there? I can see a question over here in the back. What's up? So posty infix, prefix and infix. Yeah. So you're talking about for like numerical stuff? I mean, it's not going to be more than 50% of the test, but like it's going to be more than 0%. Does that make sense? You can expect a reasonable amount, like something comparable to what was on the practice exam. Is there another question? I saw someone else have their hand up. Yeah, over here.
Are you throwing ABL trees on there as well?
Yeah, ABLs could potentially be on there. So I didn't put ABL trees on the practice test that I gave you guys because I didn't ask that on the original class, and I wanted to kind of use the data, which now that I think about it, I didn't actually like say what the good grade for that. The good grade for that class, that exam, I think was like a 6. Not like the good grade, but like the average was like a 60. So if you ended up with like a 70 or higher, you ended up doing well on that. If you ended up with like, I think it was like a 44 or higher, because like it was skewed to one direction, I forget which side, you ended up doing well. So, what's up?
You have to implement stacks, queues with arrays, because you went over it with linked list.
Yeah, I'm never going to ask you to do it with an array in this class. I'm going to only ask you to do it with a linked list. The only question I could ever do is like, what would be the pro over doing an array versus a linked list? And the idea is that a pro using a linked list over an array. So it's like the pros over an array, a linked list I discussed in class. If you're using a linked list, what's really good is that you don't have to worry about memory being all at the same location. And so like if you had fragmented memory, you could do the linked list very easily. If you had fragmented memory, it would be difficult to allocate an array, and because that would be hard to do so. I could ask a question like that. But I'm not going to like say, how do you implement this using an array, because that would be horrible. Is there any other questions about the exam currently? Yeah, what's up?
So you asked the question about the ABL trees. Are you going to be, is it going to be like adding to the ABL trees?
It could be tracing, it could be like adding things, it could be potentially removing things, it could be discussing at a high level, it could be asking you to do like a small section of code, and I mean a very small section of code. It could be about rotations, it could be about like the rules, it might be even like a runtime or like a proof. So there's like a lot of questions that could be asked on that. So everything under the sun. I saw a question over here as well. No? Okay. Okay. All right, cool. So yeah, so what are the topics? Let's do that, because a lot of people are curious about this, obviously. So we've gone over linked lists and more over like linked memory in general. We also, again, this includes lists, stacks, queues, trees. And then inside each one of these, we kind of have like our own thing that we can do as well. So what were the like linked list things that we talked about? Single, double. I did technically talk about circular, but I'm not going to ask you a question about that because I don't like circular linked list, even though some people do. It's dynamically done. We've done some insertion, deletion, some containment. So, and then like some potential runtime questions as well. For stacks. We talked about how to implement them using linked lists. We talked about how to add things and remove things. What is the add and remove operation in stack called? Yeah? Yeah, so how to push things on, which is to add things, and pop, which is to remove things. Yeah, we also have the peek operation. Sometimes it's called top. What else do we have? Did we use stacks for any things? He used it for the assignment. Yeah, there's a question in the back there, or in the middle? No? So, yeah. Yeah, post order numbers. So, like, really useful when you're doing post order. And so, like, some of the things we did with post order is we did evaluation on post order using stacks. And another thing we did with post order was we were able to turn infix into post order. And so we were able to show how to take an expression and turn it into a post order, and then we were able to figure out how to take that expression and evaluate it when it's in the post order notation. So infix to postfix, and then we did evaluation. And so these are all like fair game, and additionally it can ask you potentially coding questions on this. And then just code it for stacks and generals. And you can assume the same thing for linked lists. All right, so queues. I feel like this is not a little blurry. I'm going to try refocusing it. Yeah, I'm sorry about that. All right, yeah. I think that you're more readable. It is for me at least. All right, so queues. We did them using what? What was the overlying structure we used on it there, right? Do you remember? We did it using linked lists. You can do it using arrays, but we're not going to do that. So I might talk about implementation using the linked list. And then yeah, we have the enqueue. We have the DQ, and these are like how you add or remove things. And then what else do we have? Yeah, we have the front, which is how you first element. And then yeah, we need a back pointer as well in order to do things quickly. So to optimize, we need that back pointer. I don't really remember going over a specific example with VQs. I think I talked about how you can use it for searching for something. I talked about how you could do what's known as a BFS, right? I think I mentioned it in class, but I kind of just stopped there and like, yeah, this is something you can do to find your way out of a maze. And that's about it. So I might ask you a very simple question involving them, like how to use for solving mazes, which is a little bit crazy. I'd probably give you a very simple example of that ended up happening. I might ask you about coding, and obviously you can ask you about runtime for any of these. So this is like something that's dangerous if I do put it on there. All right. And then another thing we talked about, we did the trees. So what did we talk about when we did trees? So initially we just kind of talked about it at a very high level, right? We just talked about how you have like some node that points to some other nodes. And what type of tree have we been working with the most in this class? Binary search trees? Yeah. So, I mean, you could argue that's a binary tree or a binary search tree. We haven't really used a binary tree that's like without being searchable. Like everything we've done pretty much in class has been a binary search tree. But there are different classifications. So I do want you to understand the difference between a binary search tree and a binary tree. And the idea is that you need to understand what the search property is. Now, as it turns out, the search property, if you're doing a comparison of like greater than or equal to or less than something like that, you really can only do a binary tree. It's very difficult to do a comparison that's searchable on a tree that's non-binary, because then it gets a little bit gray over what you would consider it to be binary and non-binary. There's like one exception to that really, and that's the trees that are known as the 2-4 trees, which I didn't get to cover in class. But a 2-4 tree is a weird tree, where rather than having nodes that have like one child coming off off of it. They can have nodes with multiple children coming off of it, and then they can have multiple values for nodes. It's pretty cool. I might end up drawing an example, like at the end, just that way you can see what they look like and stuff like that. So anyway, so there's the binary tree, there was the binary search tree, there was the search property. What were we doing with trees? What type of operations were we using on them? So we were adding nodes, right? Adding is like insertion, deletion. What else were we doing with trees? We were doing ABL trees. There's like another thing I did with them actually just today. Traversals, remember those? What type of traversals do we have? Is there anything else? Yeah, so the ABL tree was really big. An ABL, what did it require to do ABL trees? Or what does it require? Rotations. So the type of rotations are left and right. You also really need parent pointers to be doing ABL trees. If you don't have parent pointers, it's very difficult to do this type of analysis. I mean, there are ways to get around doing it by using the stack to go ahead and kind of act as your parent pointers, but I think that gets a little bit too ridiculous. So I just recommend using parent pointers in general. So I know we did some other things with trees, but I can't really think of them right now. In the labs, did you do something fun with trees? Did you use them kind of as arrays? Yeah? Okay. Maybe. Hopefully you did in your lab. If you didn't do that in your lab, then your team might have given you the wrong lab. Alright. We'll worry about that on the exam. So is there any questions about the material right now, as of this moment? Oh yeah? No, there shouldn't be summation. I don't, that might be on the final, but not on this exam, because I don't recall saying that. I'm trying to think of when a summation might occur inside this section of the class.
Like another recursion problem.
A recursion problem might exist in this because the insertion in a tree is in general considered recursion. But a recurrence relation, the only reason why I would do that is if I'm asking you to prove some property. But the thing is, the binary search tree property is very simple. So the idea of how binary search tree property works for doing insertion is if you want to know the runtime for it, if you do it as a recurrence, let's say we do an insert into a balanced binary search tree. EBST insert. And suppose we know that every time we look at a value, because it's like perfectly balanced, that means that we eliminate half the nodes that we need to look at. So you can say that the runtime, the T of n is equal to 1 plus T of n, n divided by 2. And this is basically saying that we do one extra comparison and then we go ahead and reduce the size of the tree that we're looking at by half. And then additionally, we can know that T of 1 is equal to effectively something that's constant in runtime. And then I say, so what is the closed form for T of n? Like this is like a really sketchy problem. I don't think I'd end up doing, but like this could be something that you can see. I'm probably not going to ask it. But the idea is you say, okay, T of n is equal to 1 plus, so this is me trying to solve it, T of n divided by 2, and then we need to find out what T of n divided by 2 is. So T of n is equal to 1 plus 1 plus T of n divided by 4. And then we continue this. No, I don't know why these two are inverted. Now we plug this thing in the original equation. And then we can see that T of n is equal to k plus T of n divided by 2 to the k. And now what we say is, let's find out when this is equal to 1. So we say 1 is equal to n divided by 2 to the k. We know that n is equal to 2 to the k. And then we know that k is equal to log of n. Because we know k is equal to log of n, then we know that t of n is equal to log of n plus t of 1 effectively, which means that t of n is equal to log of n plus 1. And so that's how you can do a recurrence relation to prove the runtime for a balanced binary search tree contains or insert or removal, but that's a little ridiculous and over the top. And really, you can't even really say that's n divided by 2. You would have to say that's like some potentially smaller constant. And it's kind of difficult to do that analysis on a balanced binary search tree unless you know it's completely balanced. So that's kind of garbage. There's a question I saw over here. So do you still have it?
So the ABL tree is an ABST?
ABL tree is a VBST. Other VBSTs, which I was not able to cover in class, there's a red-black tree and the 2-4 tree. You'll probably learn both of those if you go to CS2. Red-black trees, in my opinion, are the most fun though, because you get to do coloring. I might end up talking a little bit about that at the end of class, just as like, hey, here's something you can also do. I saw a question back there, but it doesn't have any more. The people's names, which I have yet to look that up. So obviously we care a lot about those computer scientists. I'll do them a solid and look them up right now. Question?
Yeah, I was just wondering, what's a way to practice for coding?
A good way to practice for coding? So I would recommend probably looking at my stack code for the solution number 3. That's like a good example if you want to learn how to do stacks. And I think I might even put a queue inside that project program as well. So you can very easily look at the stack and the queue version. I don't think I'm going to ask a coding question on ABL trees because doing left rotation and right rotation is like really tedious and very error prone. I did that on the final exam of one of my other classes because I like just kind of ended up spending a long time coding an ABL tree up for them outside of class, and then I gave it to them. Which honestly, I probably should just like use that as a reference thing at this point, so that way we can like actually see good ABL tree code rather than something that I tried typing up in here. But I'd recommend like insert and remove are pretty easy, I think, to code up for a non-balanced binary search tree. So try looking at, I think I did an insert version of a binary search tree in class. I'd recommend double checking me on that though. And if you want to get practice for what a non-binary balanced binary search tree looks like without the, basically without balancing, just remove most of my code in the partial BBST, and you could probably get something there. And I saw a question over here. What's up? So this way? Let me separate these a little bit. So that's all literally there. So apparently AVL stands for Alabama Virtual Library. I feel like that's not what I wanted. Oh, okay, here we go. So Adelson, Belsky, and Landis. I'll write the name down. All right, so the test review is going to be kind of a little bit weird. I'm going to ask you if you had any questions first on the review, and then I'll go over like a few more questions after that. So did anyone have any problems with the exam review that was posted online? A few of you guys? Okay. I saw you in the middle first, so let's go ahead and do yours.
It's not necessarily a problem with the review, but I was curious.
There was a typo on one of the questions, the NQ one.
Is it the NQ?
Yeah.
I saw that one, so I was just curious, like, would you say the review that you posted is like easier than what to expect on the exam, or?
So there's not going to be a string question on the exam. The reason why I left that one in there is because that's what I had on the previous exam that I gave, the previous viewer gave it to, and I kind of wanted to use it as like a rule of thumb for like how people would do. But I think that it's going to be about the same difficulty. So it's probably going to be a little, I'm hoping it's going to be a little more clear. Because I know that the clarity on the NQ problem was apparently really difficult for people on the original exam, and it was difficult for people that were coming to my office hours a day. They're like, I don't even know what this question's asking. So, I think that it's going to be about the same difficulty. Hopefully it took you 75 minutes or less. What's up? Yeah. What's up?
Do you think the practice one is comprehensive of what we tested on the real event?
No. And the reason why is because balanced binary search trees were not on that test. I saved them basically for the final exam and destroyed people. So you can expect one of those. There's a question I thought over here as well. Did anyone have a question about their review other than that? Okay. Oh, okay, so you do have one? Which one do you want me to go over? Number 4? Let me just double check what that's asking. The right method that returns the sum of the given values of the linked list. Fine. So we're going to do a function called sum, and it's going to take in the head of a linked list, and it's going to return the sum of that linked list. And we're going to assume that's singularly linked, and we're going to assume that it's non-circular. And the head has 2 parameters. The first parameter, each node has 2 parameters. It has a next pointer, and it has a value. So I didn't give myself enough room for that. But nodes have next and value. So there's 2 ways to go about doing this. I don't think they're forced anyone to do a recursive solution, so if you wanted to, you could have used a while loop and done some stuff. But I really think that there's an elegant solution for using recursion in this. I think that the solution I posted online had the recursion, so I'm going to go ahead and do it without the recursion here, so that way you can see an alternate solution to it. So the alternate solution is we create a node star, and this is going to be a temporary node, and it's going to be equal to the head. This is actually optional, you don't need to do this, but this is what makes a lot of people feel comfortable, because sometimes they don't like changing the head value because they're afraid that might mess up the queue or the linked list or whatever you're working with. So we're just going to go ahead and use this temporary value, and we're going to have it point to whatever the head's pointing to. And now what we're going to do is we're going to go ahead and add up things while the temporary is not the end of the list. So how do we check to see if the temporary value is not at the end of the list? Yeah, you just check to see if it's equal to null. So what we can do is we can just say, while the temp value is not equal to null, we need to go ahead and add it to something. I don't really have anything here that's storing it right now. So all I'm going to do is I'm going to just put a real quick int answer is equal to 0 here. And I'm going to go ahead and say answer is plus equal to something. What should I increment answer by? Yeah, so whatever is at the temporary value, I want to go ahead and increment that value to my answer and store it, and then I'll move on to the next value. So I do temp value here, and now what I want to do is I want to move on. How would I move on? Is there anything else I need to do here? So that's going to be checked here, hopefully, right? Yeah. And now what should I were to do? So it's not that bad. Suppose I ask you something really weird. I want you to delete every other value in a linked list.
Modulus 2.
All right, how would you do that? We won't delete the first value, but we'll delete every value at basically modulo 2 is equal to 0. So, yeah?
You could add a second parameter to your sum if you're doing recursion, or if it's iterative, you can just keep another variable that keeps track of how many loops you've done in this.
Okay, that's really good approaches. I like both of them. You actually don't even need to do a second parameter to recursion if you're doing a recursion one. Let's go ahead and do a recursive solution to that. So, yeah, this is kind of how sometimes my reviews go, is I just take a problem and I try to expand upon it, and I see like how we can make it harder, which is great, right? All right, so, no, all right. So this is every other deletion. So I'm going to call it delete even. And it's going to take in a node star and a head. So this is, I'm going to do this as a recursion, and since it's recursion, what do I need to do immediately? All right, so what should the base cases be, do you think? So if head is equal to null, I do nothing. I return. Return 0. So this is actually something that I kind of messed with you guys on a little bit. So this is like an int here, but the return type here, it might be a little bit difficult to figure out what we want to do here. What I'm going to do here is instead of basically doing nothing here, I'm going to go ahead and make this be a node star. I'm going to go ahead and return the new head of this linked list, whatever it ends up being. So what I want to do now is I want to say, hey, we're going to return the new head. If the head is equal to null, then what should I return as the head? Yeah. If the head is equal to null to begin with, I'm not going to be adding any values, so I should just return null. If it's an empty list, I don't need to do anything, and I should just return another empty list. All right, so now what should I do? Is there any other cases that I need to consider if I'm deleting even values? Yeah, there's only one node. I don't need to delete anything, right? So let's go ahead and do that. How do I check if there's only one node? Can't spell head. All right. So the head next is equal to null. What should we do here? Oh yeah, okay. I was hoping someone would say return null, but all right. So return head. And why do we return head? Yeah, we don't want to delete this element. So we're going to go ahead and leave it as it is, not touch it, and we're going to move on. So now we have to have at least another element. So we have to do at least one deletion. Do you guys agree with that? All right. So what should I do to do the deletion of this element? And remember, I not only do I have to delete it, but I have to update my linked list so that way it's no longer like disconnected weird. Yeah?
You should check for two things in front of you to see if it's null. So you can link them if necessary. Otherwise, you can just delete the one right in front of you and not worry about that.
So yeah, that's a special case. If there's only two things in the list, I could delete this last element and just return. But I might actually be able to kind of circumvent having that issue. And the reason why is because this function already checks to see if the last value is null. If it is null, it returns null. So if I have only two elements and I delete this element and then I call this function on the second element, like two elements away, it's going to return that there's no values that's going to go there. It's going to potentially insert the right values because it's going to insert an empty list. So I don't actually need to do that base case. I actually don't need any more base cases at this point. But you could put one in there. It wouldn't be wrong. But we're going to go ahead and just avoid doing so because that's just going to add one more thing to this situation that I don't actually need at this point. Is there any suggestions besides this? So I suggest, what I like to suggest when you're doing a insert, delete, or remove, is you make a temporary value and have it point to something that you're going to be adjusting because you don't want to lose reference to it. So I'm going to go ahead and make, because we're going to be working with the next value of head, I'm going to make a temporary value that points to that so that way we don't lose that. So node star temp is equal to head arrow next. So now with this in mind, I can very easily work with the temporary value and work with head's next pointer and not have to worry about losing reference to temp. Remember, we want to eventually delete this. So is there something you guys recommend that I can do at this point? Head points to temp next. Is it head points to temp next, or is it something else points to temp next? Yeah, head next should point to temp next because we want to remove that value. We want to basically have the temporary is pointing to the second element in our list, and we want to point to the third element of the list. Like we want the head next to be pointing to the third element, which is going to be the element after temp. So we want this next value to be equal to the value after this one. So we say head next is equal to temp next. Is there something else we should do? Yeah, we should delete temp, so we can do that. Is there anything else? Yeah, we can set it equal to null, so. There's one more thing we're missing. Yeah, we need to actually do the recursive part of this. So we need to call the function again. What should we call this function on? Yeah, we're going to call it on head next. And then we should return head. And that's all we need to do. So this is how you delete even values inside a linked list. What's going to be the runtime of this method here? Yeah, there's a question? Yeah, it's going to return something, but the beautiful part about C is that if you return and don't assign it to anything, it doesn't care. So in the original sum function, we don't need to do it. And the reason why is because in this one, we want to delete values, because this is a delete even. In this one, we don't want to modify the linked list at all, because we want to just sum up the values. We don't actually want to change anything. Like the topology can stay the same of the linked list. And here, we need to change how the connection is going on. Is there any other questions? Yeah, over here.
How did you make sure it was only deleted even?
Yeah, that's what I'll.
So the reason why is because we're freeing the temp value, and the temp value is the head's next value. So because we're not freeing the head, we're only freeing head next. That means that head hasn't been touched. And now what we're doing is rather than going ahead and calling this function like on head again to potentially delete even more, we're calling it only on head next. So we're basically moving over to the next spot in the array, and the idea is, or not in the array, but in the linked list, and now we're calling the function on head next, and the idea is that head next, or this function delete even, doesn't delete that first element. And so head next is not going to be deleted, the value after it's going to be deleted. And because the value after it's going to be deleted, when we go ahead and remove it and we shorten the list, we then call the function on the next value. So we call the function on 1, we then call the function effectively on 3, we delete 4, we call the function on 5, we'll delete 6, we'll call the function on 7, and we'll only call it on values. And the only values that end up getting deleted because of this are even. Is there any still confusion as to why this only deletes the even values?
No, I think he might have been using what I thought was
Okay. Oh, values that have even values? Oh, yeah. So no, I was saying like every other deletion, which means you delete every other value rather than delete even values. I know that, yeah, that's a little bit confusing. So this is like, I meant like even index, not even values. All right. Are there any other questions? Yeah, what's up? Number two, what was it? Deletion in the binary search tree, and that's at a high level, right? So, in the binary search tree code, I've talked about deletion a few times already. So how binary search tree deletion works, there's 3 cases that generally occur, but the idea is in order for those 3 cases to be considered, you first have to actually get to your node, because the node might not even exist inside your tree to begin with. So we need to first find the node, and how you find the node is if the value you're looking at is equal to your value, you found the node. If it's not equal to the value, this is supposed to be delete by value, not by like something else. If it's less than your value, you're going to have to, that you're trying to delete, you go to the right. If it's greater than your value, you go to the left. And then you just basically recursively call this every time you get to a new node, and you either go left or right. So once you find the value inside your tree, you then have 3 cases that you have to be part of. Does anyone remember what the 3 cases are for deletion? Yeah? What? No child? 1 child? 2 children. All right, very good. And the reason why, because this is a binary search tree, so you should only have either 0, 1, or 2 children. So let's go ahead and just talk about this from the top. So find the value first. And this can be done by if at value. This is to be deleted. if less than target. Did it get out of? It's my hands are like terrible. They like, I don't know what they do. They mess up with the contrast. I've actually tried this before in other classes. I'm sorry. Wait, why can't I put my hand here? Okay. Alright, I'm gonna try that. So it's less than target. Is that really bad? Alright. Yeah, it doesn't like my hands. I'm sorry, guys. Alright. So if less than target, we delete. So if our node is less than the target value, then that means we need to delete in the subtree over here. So we need to delete in the right subtree. If we're greater than the target, then that means this value is too big, which means we need to go into the left subtree. And then if this value is null, then we can't really delete. That probably should be like moved up to the top, but whatever, not important. This is supposed to be at a very high level anyways, so I'm already kind of going into too much detail. This is like just if you want to be like super critical. So then case 0, no children, or case 1, depending on how you want to call it. Delete node and set pointer to null for the parent. This is already like a lot more. If you just put delete node, I would have accepted it. So in case 1, we have one child. We replace original with child, delete original node. And then case 2, 2 children. And so this one is the hard one. We find replacement, swap, delete original value in replacement subtree. And this is like very high level. This is all acceptable though. Is there any questions about this? Yeah?
You arbitrarily choose which children to allocate to place.
There's only 2 possible values you can do this one way. You can either do your minimum value in the greater subtree, because that's going to be the closest value to you, or you can do your maximum value in the lesser subtree, because that's going to be the closest value to you. You always need to replace with the value that's closest to you, and you know that there's going to be a value that's closest to you in either one of those 2 subtrees, because you know that neither of the subtrees are empty, you have 2 children. So there always is exactly 2 values that you can do this swap with.
Right. I'm arbitrarily choosing.
Yeah, as long as you choose one of those 2. So it doesn't matter. You can like have a random value that you're like flipping to and figure out what you're doing.
Left and right.
Yeah, just as long as it's in one of those 2 subtrees. All right. So what's up?
So for this question, which is number 2, then for your one child, you put next parent with child.
Yeah. So connect the parent of this current node with the child of this current node, and that's basically removing it. So I know this is a little bit weird because that sounds like you're not doing anything special, but the idea is that you have a parent node and you have a child node. That parent is not the parent of your child, right? Hopefully not, because I think that you've done something terrible in terms of gene pool at that point. I'm sorry if like anyone's in that situation, but the idea is that that parent is your child's grandparent, and so you're connecting your child's grandparent to your child, and you're basically removing yourself. And so that's why it's worded that way. It's correct. And I know that's a little bit confusing. I'm hoping that this clarifies things a little bit for you.
That's what I just wanted to.
Yeah. Is this more or less clear than what was on the thing online? About the same? Okay, cool. All right, is there any other questions about the thing online? Otherwise, I'm going to go ahead and do another problem. Convert this into postfix. And then we're going to do one more. Yeah, well, we'll do that in one moment. I'll let you guys work on that for a little bit. If they have the third line going through it, it's a multiplication. So this here is an x. I'm going to go ahead and put little doohies there. Woohoo! That's confusing. All right. Because I am a masochist. Not going to argue about logic. All right. All right, so this is an infix, and I want you to turn this into postfix. And this is a postfix, and I want you to turn it into infix. Yeah, they're x's. You guys are really making me sad. All right, what's up? I don't have a preference. Where you're working at, you may have a preference, but it's the same theoretically. Either way. Whichever one you put, it doesn't matter. Like if you want to be like concrete and say you choose the max value in the min subtree, then I'll understand that. So what's up?
Y1?
Yep, y1 plus divide. I don't hate you guys. I want you guys to do well, so I'm giving you really hard questions here, and hopefully you'll do well in the exam. You have another question?
When the division goes into the stack, the x comes out and the minus goes into the stack, since the division has priority, the minus will come out, and then the division will come out and the minus will go into the stack, right?
You're talking about in here?
The first one.
The first one? There's no multiplication, so yeah, let's go ahead and do the first one now. I feel like I gave you guys enough time to do that on your own, and I think we literally have only 5 minutes left, so. All right, I can do this though, that's not bad. All right, so let's go ahead and do this. So we're gonna work with the first one. So the idea is that we have to put the parentheses into the stack, because that's how this rule works. Normally you would, normally you'd put it on top of the stack, but since the stack is empty, it's the first value that goes into the stack. Not very interesting. IMO. All right. So now what we do is we get to the next value, which is y. What happens when we run into an operand? Do you guys remember? Yeah, so we output y, and then we get to the plus sign. What do we do with the plus sign? We add it to the stack. We get to the z, what do we do? Output it. All right, we get to this closing parentheses, what do we do? Pop everything, so we pop this plus sign, and then we pop the open parentheses, so now we have an empty stack, right? Nothing in here, sad. All right, so now we get to divide, what do we do? Put it on the stack, we get to this x, what do we do? So we output x. We get to this minus sign, what do we do? Yeah, we're going to pop the divide, and then we're going to store the minus sign. So we now have a stack with just the minus sign. Why didn't we push this minus on top of the divide? The divide has a higher precedence, so it needs to occur before the minus sign does. So we need the top of the divide off because it needs to happen before the minus. Try to keep that in mind. If it should occur before because of precedence, then it should come before in the string. The divide should definitely occur before the minus. The reason why the plus is occurring before the divide is because the plus was in the parentheses, and the parentheses said you are a higher precedence than this divide operation. All right, so now let's move on. So we get to the C, what do we do? All right, and now what do we do when we're at the end of the string? Pop everything else on the stack, so the minus comes out. So the string will end up being yz plus x divide c minus. So if you don't believe me, we can go ahead and run through this and see what happens. So let's go ahead and run through this. We evaluate this here. We do y plus z. And now we have this y plus z that's like kind of in this parentheses, and we have to do the divide by x, so x goes on the bottom. And now that's everything that's in here, and now we have to subtract c from it, because that's what this minus c means. So we put a minus sign in the c there, and that's how we end up finishing the expression off. And that's kind of what we have up here, just written like more mathematical and a little less in tricks. So now let's go ahead and take a look at what's going on up here. So does anyone have like a solution to this thing?
Wait, so if you didn't do the y plus z over x minus c, the question will be wrong.
You don't have to do like strictly over. Oh, are you talking about this up here?
Yeah.
So what we're going to probably evaluate for partial credit is that you got your postfix stuff correct. So if we see that you're adding like a y plus z together, then you'll get credit there. If we see that you're then dividing that by the x, then you'll get credit there. And if we see that you're subtracting c from it, then you'll get the full credit at the very end. If you subtract c from something else, you'll probably get partial credit, but not the whole thing. Like if you kind of screwed up the ordering in here, and you got the c minus at the end, you'll get some of it, but not all. Does that make sense?
No, I'm saying you can draw the box.
Oh no, this is not necessary. I was just doing that to double check. That's double check. Don't panic. Or do, I don't know, whatever you want. I'm not your parent. All right, so now what's going on up here? What do we do? Yeah, that's a 1. Oh, there you go. Well, it can be an L or a 1. It doesn't change the answer too much. Yeah, what's up? I don't know. Is the answer correct?
Yeah, because I just kind of taught myself a different way to do it where I don't draw the stacks and I don't write it.
Okay. If I say draw the stacks, then you'll lose points. If I don't say draw the stacks, then you'll probably end up with credit. So is that a risk you're willing to take? Yeah. Okay. It's okay. We can. If you need help, I can go ahead and probably give you more practice problems to work on tomorrow. But don't problem. All right. Let's do the last one because we have like 30 seconds left. So what we're gonna do in this problem here is like really hard to think about what's going on here because normally we're able to just perform the operations pretty easily. So the idea is we should have an operation stack or operand stack. So 1 should be the first value in an operand stack. Then we put x in. Then we put x in again. And now we have to multiply these two together, and then so that means we should remove the x's and then multiply them together. So I'm going to go ahead and really simply say that that's like x squared, because that's what happens when I'm using this multiplication. And now I need to do this minus sign. And so in order to do this minus sign, that means I need to go ahead and pull out the x and the 1, and I need to do this subtraction between them. And then I'll put it back into the operand stack. And so this is what the operand stack looks like after the minus sign. And then I push the y in, so the y goes up here, and I push the 1 in as well. And now what happens is I get to this plus sign, and when I have the plus sign, I need to pop these two values up here, and then I need to perform the operation of plus on them and put it back into the stack. So I pop the 1, I pop the y, I add them together, I have a 1 here, plus y, and then I have 1 here minus x squared. Technically it would be like y plus 1, but I don't think I'd take off points because it's the commutative property of addition. And then the last thing we end up needing to do is we need to do the divide. And so when we get to the divide, we need to pop these two values off. We need to perform division on them and then stop. So y plus 1 was technically the later value. So this is going to be technically the first value we're going to perform the operation on. So we should do y minus x squared divided by y plus 1. And this should be the final value. If you didn't write it that way, if you wrote 1 plus x times x divided by y plus 1, then that's okay as well. But it really does need to be something like this, where I understand what's going on. That. All right. Yes, it is. Something like that. All right. Is there any other questions right now? If you do have some, yeah, there's one over here.